Hi everyone, thanks for joining me today for this session, which is about maximizing growth through event-driven architecture. My name is Talia Nasi, and I'm a Senior Developer Advocate for AWS Serverless, and my job is to build serverless things and then teach the world about them. Before becoming a developer advocate, I was a test engineer for a few years. I worked at Visa, Forbes, and WeWork. My Twitter handle is also here in case you all want to contact me or follow me for more fun stuff. We have 45 minutes today, and this is a 200 level talk, so I'm going to cover 7 areas. First, I'll go through an introduction to serverless and what it means to be a serverless application. Then I'll introduce events and Amazon EventBridge. I'll cover events versus APIs, and then we'll talk about using EventBridge with AWS SAM. Then we'll get into the benefits of event-driven architecture. And lastly, we're going to play with Legos. Just kidding. We're going to talk about how Legos use serverless to scale. So when we say serverless, we mean it's the removal of server operations. And this is an important distinction for customers because it allows you all to focus on the building of the application rather than the management and scaling of the infrastructure to support the application. And these are the 4 tenets that define serverless as an operational model. Firstly, there is no infrastructure to provision or manage. There's no servers to spin up, operate, patch, feed, water. Serverless applications automatically scale by unit of consumption rather than by server unit. And automatic scaling is a really big win for companies because generally you create multiple MVPs and you don't want to build all of them out for scalability. Serverless also has a pay-for-value billing model, which means you only pay for what you use, not for idle time. So if you have an idea that's not taking off, some of them can get expensive. And this also means that you can experiment more. So let's say I have an idea for a new feature and Eric has a competing idea for a new feature. Eric and I can A/B test our features, and regardless of which feature has a higher conversion rate, it's not going to cost us much because you're only paying for what your customers are using. Lastly, serverless applications have built-in availability and fault tolerance, so there's no need to architect for availability because it's built into the service. And this is important, right? Because things will break, unexpected things happen. You know, there's outages, there's earthquakes, spaghetti and meatballs can fall from the sky. So what do you do if the servers handling your project fall over? How do you know that all of your versions are in sync with all of the regions? Have no fear, serverless is here, my friends. So this all happens automatically. At the center of serverless is AWS Lambda. It's a serverless product that is the core of a few terms: event-driven computing, functions as a service, and it's serverless, which means it meets our 4 qualifiers. AWS Lambda lets you run your code without provisioning or managing servers. You only pay for the compute time you consume, so there's no charge when your code is not running. With Lambda, you can run code for virtually any type of application or backend service, all with 0 administration. All you have to do is upload your code, and Lambda takes care of everything required to run and scales your code with high availability. You can set up your code to automatically trigger from other AWS services or call it directly from any web or mobile app. But Lambda doesn't just sit in a vacuum by itself. It's one of the parts of a serverless application. And typically with Lambda functions, there's 3 parts. There's an event source or trigger, and then you have the actual function, which is your business logic, and then you have the services or the destination. And so an event source has a number of services that can directly interact with Lambda. And an event can be almost anything. And we're going to talk about this a lot today. It can be an HTTP call, it can be a cron job, it can be something uploaded to an S3 bucket, it can be a payment arriving through Stripe. The event is something that happens and it's what causes the Lambda function to come to life. And then you have the Lambda function, which provides your business logic. And then you have the destination, and that can be whatever your code needs to interface with. And this is entirely up to you. It just depends on your requirements. So an example of this workflow would be like a customer pays for something, the payment gets processed, and then now they have access to whatever service. So now I want to go through events a little bit more in detail. And let's start with a very successful event-driven application. The example is this website we run named after a river in Brazil, and I'm guessing a couple of you have visited this site before. The main objective of this site is to get you to click on the Place Order button. Once you press on that button, a couple of things happen. First, we check your credit card to make sure you can pay. Then we have to get the merchandise off the shelves and onto the trucks and so on. And all of that happens in an Amazon warehouse. There's no synchronous API call for the Amazon backends to package and ship products. What the front end does after your payment is confirmed is it puts together some information describing the event and puts your account number, credit card info, what you bought in a packaged event and puts it into the cloud. Later, another piece of software will pull it off and start the packing, shipping, and all of that. And the key point about this process is that all of these things can run at different rates. And normally the rate at which people click place order and the rate at which the warehouses can get the boxes out of the doors are roughly equivalent. But on days like Prime Day, Black Friday, things like that, people hit that button immensely faster than the warehouses can operate. And that's okay. The back end will work itself through. So this is very clear event-driven architecture, and it's a relatively new concept in the cloud because before it was common for developers to use APIs to build their applications. APIs are used to talk to services, and it defines how the services should exchange information. So normally when you first think of how to build your applications, you don't think to use events or event-driven architecture, you think to use APIs, right? And I just want to go through some of the differences between APIs and events. So API thinking is synchronous thinking. You can't move on until the API response comes back, right? With APIs, you're sending commands, right? Go do this thing. It has an intent and it's directed to a target. So create this account, add this product to the shopping cart, right? Like go do this thing. And an event, on the other hand, is something that happened. Maybe a new file has been created. Maybe an exception or error occurred. Maybe a new customer has been created in the system. Maybe a new order has been inputted into the system. It tells you a fact. They're immutable, which we'll talk about in a second. And in practice, it's just a JSON object that tells you something that happened. And a lot of people get scared when they think of events and how to use them, but all it is it's an envelope with a description of what's inside, and then inside that envelope is just a JSON describing what the event is. So again, with events, you're telling a fact, and others decide what to do with it. Request-driven applications that use APIs typically use directed commands to coordinate downstream functions to complete an activity and are often very tightly coupled. On the other hand, event-driven applications create events that are observable by other services and systems, but the event producer is unaware of which consumers, if any, are listening. And these are typically loosely coupled. So let's go through a quick review of some of the challenges of microservices. So this is a standard synchronous API. We've all written plenty of these. Basically, the customer just comes in, the client just comes in and says, hey, I want to place an order. The order service sends the request downstream to an invoice service. And if it's successful, it responds back with a success message, confirmation number, etc. Great. So in this initial stage, these are decoupled and everything is super simple. But what happens when you add more services that integrate with the order service? The order service has more responsibilities and more complexity. The order service must understand retry semantics for each service and bundle in an SDK for each. Even if each downstream service publishes the API, the order service is responsible for talking to each of them. And if there's any backwards compatible changes to the APIs, the order service team is on the hook to update. And long term, there's going to be more systems out there that need data from the order service. And in this model, those teams are blocked by the order service team to implement. And so they can't operate independently as they once could. So now there's this unnecessary friction in the process due to the integration cost of hooking the services together. And this is going to slow down your development process. So here's the same e-commerce application with some additional downstream services, fulfillment and shipping. In the happy path, everything works as expected. The order service triggers invoicing, payment systems, and updates forecasting. Once the payment clears, it triggers the fulfillment and packaging of the order. And now you inform the shipping service to request tracking information. But what if the fulfillment center can't find the product because they're out of stock? The fulfillment team might have to alert the invoice service. and then reverse the payment or issue a refund, the shipping service might have been already triggered. So that could be another message to fix that. And forecasting could be broken or wrong, or maybe they'll just accept an adjustment. And this remediation workflow is all just to fix one of the many potential unhappy paths. Here's another one that happens more often. Imagine your team works on the payment service, but you weren't told that another service or reward service was added. What now happens when the fulfillment service errors? Fulfillment maybe orchestrates all of the other services. So your payments team gets a message and you undo the payment, but you don't know who's responsible for retries and error logic. The end result is that the reward service might never find out. So the reward service thought that they integrated correctly with the order service, but a canceled order results in a reward for a customer account. Now, what happens if the reward service changes vendors and has a new API? Did your team know about that? The old service is pinging the new service to keep it in sync. So ultimately, it's really hard to coordinate these orchestrations and workflows as systems become more complex and services are added. So those are the challenges with microservices, but there's also some benefits to using microservices, and let's talk about those. So in a well-designed microservices architecture, you can maintain loose coupling between the services. Microservice-based systems can be significantly more scalable. Indeed, many AWS services are microservices-based precisely because of this. You can build systems that are much, much more extensible because new features and applications can consume events without impacting existing systems. Much of the complexity of large systems can be easier to manage in a microservices model. And of course, you can design for higher levels of availability with many patterns available to help develop resiliency and fault tolerance. So how can events help with the challenges of microservices? Like we talked about before, in the simplest terms, an event is a signal that a system's state has changed. Events are represented as JSON, and the attributes of an event are that they are facts. They are also immutable. So once it's done, you can't unring the bell. For example, if a customer places an order and then cancels it, that's two separate events. Once the order happens, you can't undo it. So if you want to cancel it, you create another event. Events are also observable. So anyone who's authorized can watch an event. So think of a coffee shop, for example. You have a barista and a pastry guy. If I come in and order an espresso, the barista is going to respond, okay, I'm on it, I'm going to get your espresso, and the pastry guy doesn't care about that. However, if I come in and order a chocolate croissant, then the pastry guy gets up and says, okay, I'm on it, I'm going to go make your croissant. The barista doesn't care or respond to that. Events are also temporal. So all events have a timestamp. If you imagine you're at a coffee shop and there's orders at 1 p.m., 2 p.m., 3 p.m., sometimes orders that are later in the day don't get fulfilled because you run out of inventory. With events in AWS, there's a feature called archive and repeat where you can simulate a day's worth of events. And so when your code falls over, how do you know what happened? And so using this you can take the day in question and feed it through your system in debug mode and figure out what went wrong. So again, people think events are scary, but it's just JSON. And if you can write JSON, you can write an event. Events are asynchronous. So in a synchronous model, like in that example before, the client made a request to service A turns around and calls service B, but then service A sits around waiting for service B to finish doing whatever it has to do before it continues on and eventually responds to the client. In an asynchronous model, there's no response path. The service surfaces the event and then immediately moves forward. The obvious trade-off here is that there's no channel for service B to pass back information to service A, but in a lot of cases, it turns out you don't really need that explicit coupling between the request and response channels. Events are observable, not directed. So again, think of the coffee shop example here. In the previous tightly coupled APIs, we used directed commands, right? Whereas in an event-driven approach, you have observability. And so what's the difference between the two? In a command model, each command is explicitly used to a specific recipient. If you send a command to create an invoice, you wait for the response to come back with the invoice. Events, on the other hand, are merely observable by other systems. So if there's an event saying that a customer just ordered a small latte, other systems can observe that and act as necessary. So the barista can go in and start making the small latte, but the pastry guy is not going to care. The benefits here are that event producers don't need to have any knowledge about who's listening to those events, and that keeps them really simple. It also allows other services to consume events without needing upstream changes. But how do we actually implement that? How do we pass information from the order service to all these other downstream systems without actually calling them directly? For that, we have what's called an event bus. An event bus provides an endpoint where an event producer can send events. The router manages directing and filtering those events to the appropriate downstream consumers, and consumers can get the events they care about reliably while producers remain decoupled. So now our architecture looks like this. The order service sends events to the bus, which is configured with rules that determine which downstream systems get the event. Some targets only care about certain events, and others want all of them. Either way, the router now takes on that complexity of ensuring these events get propagated appropriately to each downstream service. Back in our example with an event bus decoupling the architecture, it looks similar, but if the fulfillment has an error, they raise an error event. And this is caught by other services that are listening and can take action accordingly. And in the other problem example where a reward service is added, for another team to consume some other services events, they just add a new rule to the bus. There's no need to wait on the order service team to make an update for them. And so now the service teams can act more independently and move faster. At Amazon, we have a name for our event bus service, and it's called Amazon EventBridge. Cue the fireworks. With Amazon EventBridge, your services can both produce messages onto the bus and consume messages that they need from the bus. And the services don't need to know about each other, just about the bus. EventBridge is a serverless event bus service, which means it meets our 4 previously discussed qualifiers. Some of its notable features are that there's no infrastructure to manage or provision, scaling is handled for you, you only pay for what you use and you don't pay for idle time, you get native integrations with many Saas providers, traffic travels internally within AWS infrastructure, not on the internet. It also integrates with over 180 AWS services as event sources and 18 services as targets. And the cost of EventBridge is $1 per million events, and there's no charge for events sourced from AWS services, and there's no additional cost for delivery. Let's take a look at some integration patterns that you can build with EventBridge for your serverless apps. EventBridge accepts events from event sources, and these can be any one of our 180 AWS services. It can be your Lambda functions and applications. It can be custom events. It can be Saas application providers like Auth0, Datadog, or PagerDuty. Then there's 3 types of event buses. There's a default bus, which is always available in every account where AWS events are routed to. You have your custom event buses, which you can create for your own applications, and you have Saas event buses, which are created when you configure Saas applications. There's many potential targets, including Lambda, Kinesis, step functions, API gateway, EC2 instances, SNS topics, and SQS queues. You can also route events to buses in other AWS accounts. This flexible design allows you to create a wide variety of integration patterns based on your specific needs. So the first example is a scalable webhook. A webhook is an HTTP endpoint callable from another service, which could be another microservice or third-party app. Webhooks are often public endpoints that can receive sudden bursts of traffic. If the backing application cannot scale, it can experience an outage when traffic surges occur. In this case, the caller of your webhook may not have retry or error handling logic, and you can lose messages. EventBridge provides a simple solution. In this architecture, the HTTP endpoint routes directly to an event bus using a service integration. The HTTP API service integration passes events directly to the EventBridge service, and the bus then passes the messages to an SQS queue for durable persistence. In this example, a Lambda function then processes those events. You can change the destination of the webhook easily by adding new targets. You can also control the rate of consuming events in the Lambda function via the batch size property and concurrency controls. How is this configured in an AWS SAM template? So on the left, we have the HTTP API config, which uses this OpenAPI specification shown on the left. This defines EventBridge as the target and specifies the credentials used. It also specifies how the request parameters in the API call are mapped to the JSON body of the event. And in this example, I've mapped the detail type, and source attributes for the event bus. On the right, you can see the EventBridge rule, which is configured to filter for a source of my webhook to match events from this HTTP API endpoint. It then defines the SQS queue as a target. You can download and deploy this example from the GitHub repo shown on the screen. The second integration pattern that's interesting can help you respond to workflows. So in the opening example, I showed an e-commerce application with these 6 services, and some of these services, like payments, may have their own complex logic internally. So if you think about payments have different types, right? There's cash, check, credit, and they can succeed or fail. They can be reversed fully or partially, and they may take a long time to complete, like days or even weeks. So the payment service would be a really great candidate for step functions given the complexity of the workflow. A workflow that emits events for all the other different statuses is useful for extensibility and allowing other services to respond to changes. Integrating step functions with EventBridge allows you to do exactly that. As state machines begin and end, or steps progress, it can emit events to the bus. So there's no cost to do this since the events are sourced from another AWS service. And so if there's nobody listening to the event today, that's fine, but it gives you the capability tomorrow and allows other teams to build. And again, we have this GitHub repo if you want to see how to deploy a step functions workflow, emitting events to EventBridge, and then creating rules for a Lambda function. The events emitted from the workflow look like this. So the detail type shows a status change. It provides relevant ARNs, timestamps, inputs, and other data. So to consume an event that's interesting to your app, you simply build a matching rule. So unlike the order invoice example I showed earlier, this allows integrations without code changes in your software. It allows other teams to build their own services based upon your workflows. As the event producer, you're enabling the capability by creating the event, but you are not responsible for their application. This third example uses CloudTrail to source events. Many AWS services and actions can emit events to EventBridge. This includes services like AWS Batch, Code Build, AWS Glue, IoT Greengrass, and many more. It also includes actions like sign-in events from the console or tag changes on AWS resources. You could use those to build a serverless workflow to take action when a user logs into the console or take action when tags change on resources. Beyond those supported events, you use EventBridge with services that do not emit events by using AWS CloudTrail. EventBridge can listen to any events logged in CloudTrail. All events that are delivered via CloudTrail have a detail type attribute of AWS API call via CloudTrail, and so this opens up a variety of useful integration patterns. One example is allowing multiple S3 buckets as an event source for a Lambda function. When you use the default integration between S3 and Lambda, you cannot have overlapping subscriptions. If one bucket is publishing all events to one Lambda function, you cannot create a second Lambda function with the same subscription for the same bucket. However, if you enable CloudTrail logging for your S3 buckets and consume this event source in EventBridge, you can use overlapping subscriptions. This means you can have several buckets trigger one or more Lambda functions, or you can have the same prefix or suffix patterns trigger multiple functions. After enabling CloudTrail, you can then create an EventBridge rule to define which bucket events should trigger the function. So in this example, the event pattern filters for put object events on 3 named buckets. You can modify the behavior of when the Lambda function is triggered simply by modifying the EventBridge rule. You can take this a step further by using content filtering syntax in EventBridge rules. Imagine, for example, you need to invoke a Lambda function when an invoice is saved in a monthly sales bucket. These buckets follow the naming convention, my sales, and then the month. To do this, in the event rule, you can simply use the prefix operator to match any bucket beginning with my sales. And then the native S3 to Lambda event source mapping only allows you to map functions to existing buckets. So this approach allows you to dynamically map events even for buckets that aren't created yet. So when new buckets are created, my sales April, my sales June, etc., matching events from those buckets will trigger the function. CloudTrail logs provide additional information about S3 events such as object size, principal, source IP address, and many other attributes. You can filter on these using complex rules to match specific sets of events. Then your rules can trigger Lambda functions, step function workflows, and any other target that you need. Take a look at the code repo to see how this works in detail. Many of our customers use SaaS services as essential parts of their IT infrastructure. One of the most interesting features of EventBridge is the ability to integrate with these software as a service solutions. This enables a wide variety of patterns. There are currently 30 partner integrations available from services like Auth0, Epsagon, Freshworks, PagerDuty, Symantec, and Thundra. If you're developing SaaS solutions, you can also apply to become an integrated partner. It's a fairly simple process. This integration replaces the typical polling and webhooks integrations that are commonly used to retrieve data from APIs. Polling is a compute-intensive approach to fetching data updates. It's not real-time. It doesn't work well for larger payloads. Webhooks can be difficult to scale, often only having static API key-based security, and they create a publicly callable endpoint that you must secure. This integration replaces both of these methods. So instead, events from the partner SaaS application appear directly in a partner event bus from your AWS account. It allows you to treat this data the same way as any other event from AWS services or your own applications. You can apply rules and targets to these events for further processing. This solution is much more secure since your data is passed from the provider event bus to your event bus without using API keys over the internet. It's also fully managed and scales automatically. Once you've configured the integration, there's nothing to maintain or manage. It provides a robust, near real-time, and simple way to bring events from SaaS providers directly into your apps. 3 really useful integrations to highlight here also show the coding patterns needed for any of the integrated partners. So if you use Shopify, you can consume inventory, ordering, and payment events, for example. For Zendesk customers, you can receive events, maybe run sentiment analysis on tickets, and update urgency levels as needed. And with BuildKite, you can integrate with events emitted from CI/CD processes. So when you combine the capabilities of these SaaS providers with AWS services and your own custom code in Lambda, it provides for virtually limitless extensibility. One of the benefits of having all of our events from our various microservices in one place, our central event bus, is that we can now build an analytics pipeline that uses these events to report on what's happening in our business. To do this, we set up a catch-all rule that takes all of our business events and sends them to an S3 bucket. Once the events are in S3, we can use Amazon Athena to query the events, and these queries can produce data that can be added to a dashboard in Amazon QuickSight, which our internal teams can use to keep track of how different areas of our business are performing. The other benefit of having all of our events in S3 and queryable through Athena is that we can easily debug any issue in our application. Say, for example, an order didn't get processed by our warehouse service. We can hop into Athena, run a query for the order ID, and see all the events related to that order. Here are some more common EventBridge use cases. You can use EventBridge as an event source for Lambda to take action based on a specific event. So the event happens, that fires a Lambda function, then it goes and does something with another service. You can also do things like workflows, which we just saw. Let's say an order is placed by a customer. You could use that order event to cause a payment workflow with step functions that might run their credit card info. You can also integrate artificial intelligence and machine learning services like Amazon Comprehend and Amazon SageMaker. Let's say a customer opens a ticket with Zendesk and they are not happy. They use profanities, maybe some very strong negative wording, you want to catch the really aggressive customer service tickets and escalate them. Those events call Lambda, and they use comprehend for sentiment analysis and then take action on them. When you integrate EventBridge with Kinesis and Athena, you can audit and analyze your events. If you have all of these AWS services splitting out events, you might want to analyze things to be compliant with your industry standards. And EventBridge is integrated with AWS services automatically, so you can take your events and put them into Kinesis, drop them into S3, and then use Athena with them. You can filter events, send them to S3, and do whatever you have to do with Athena. If you integrate EventBridge with DynamoDB, you can synchronize your data. Something else you can do with EventBridge is use the AWS Serverless Application Model, or SAM, to decouple your workloads. SAM can help you build out and deploy serverless apps using YAML templates that transform YAML to CloudFormation. It's an infrastructure as code tool so that you can create repeatable, versionable deployments of infrastructure. There are several benefits when using SAM with EventBridge. First, you can build smaller microservices that communicate using events and you deploy with SAM. This can help with simplicity. Second, if your organization has teams of developers working on separate services, it allows each team to be in control of their own service and operate independently. SAM can make it safer and faster to deploy new versions and features of your software. And since many developer teams now develop more features and services more often, building microservices that emit events helps with extensibility, allowing other teams to consume events to develop their own apps. And when you build these decoupled microservice-based apps that communicate with events, it can be easier to understand the interactions of services and see what each service is doing, compared to monolithic alternatives. Now it's time to play with Legos. So in July 2019, shop.lego.com transitioned to serverless on AWS. Lego builds with an event-driven design, and they do it nearly all on EventBridge. So back in 2017, Lego had a monolith, but after a Black Friday sale crashed their entire system, they were looking for something that was more scalable. They began decoupling their backend and building an event-driven serverless application and succeeding. So in July 2019, they announced that Lego was serverless on AWS, and the next day, we at Amazon launched EventBridge. EventBridge was perfect for the event bus model that they wanted to achieve. And so Lego rebuilt their checkout event processing with EventBridge, as illustrated here. They have a much simpler way to operate their events. With Lego's serverless-first approach, they use many AWS services to achieve their event-driven architecture. They have over 150 Lambda functions. They use more than 25 different microservices. They use all of these different services to create their serverless application. Lego took advantage of the scalability that event-driven architecture provides. They had $6 billion of revenue in 2019 and continue to grow Lego.com. They have hundreds of stores worldwide and a growing digital portfolio. Because they use serverless architecture, they don't have to worry about scale. To recap what I've shown today, EventBridge can help decouple your microservices, especially as they start to grow. The event bus separates event producers and consumers, helping to pass and route messages. It also helps with scalability, scaling up and down automatically with traffic. This can be used with other services like the scalable webhook, a pattern providing for resilience behind an HTTP endpoint. Extensibility is an important benefit as well. You can consume events from a growing list of Saas partners, and you can emit events from our applications and step functions workflows. This allows other development teams to build new applications and for your team to create new features in the future without impacting existing code. EventBridge also has a deep integration with IAM to provide granular control over event buses, rules, and targets. You can use Amazon's Serverless Application Model, or SAM, as an infrastructure as code tool to accelerate development and automate deployment. When you combine SAM with EventBridge, you can use SAM to break apart larger apps into smaller decoupled services that communicate with events. Now, in case you haven't been paying attention at all for the past 40 minutes, I want you to take away 3 things about event-driven architecture. The first, you should use event-driven architecture if you want to decouple your microservices, you want to scale faster and more efficiently, and you want to deploy faster. And if you're like me and you can't get enough of serverless, head over to serverless-land.com where there's more resources, blogs, videos, workshops, and learning paths to help you learn more about developing serverless solutions on AWS. Thank you so much for your time today. My name is Talia. I'm a Senior Developer Advocate for AWS Serverless. Please don't hesitate to contact me if you have any questions about building serverless applications, and follow me on Twitter for more content.